Hey guys, I'm Miss Neal, and hopefully, if you are watching this video, you are here for the Nature of Science PowerPoint and the Nature of Science presentation. So today we're going to start off with the Nature of Science. This PowerPoint goes along with the notes that look, that's time I need a copy, the notes that look like this. So let's go ahead and get started. I'm going to make myself smaller and put myself up in this top corner so you can still see me if you need to, and I'm going to have these slides big right here in the middle. All right, so the first thing we're going to talk about is the method of science. So science is a process that uses observation and investigation to gain knowledge about events in nature. We want to write down what we see, we want to write down what we observe, and we want to write down what we can investigate. Does the change in temperature affect that? Is it better hot? Is it better cold? Is it fast? Is it slow? Those are all things we can investigate. We can also use observation for science. I can look out of the window of my classroom and say, it's sunny outside today. That's science. Whether you remember elementary school science or not, that is science. So you're going to write down this definition and that first blank on your fill in the blank notes. So the scientific method is an organized set of investigation procedures used by scientists. We all use the same methods over and over again. That way our experiments are reproducible. Our results aren't valid. They're not good unless somebody else can do exactly what we did and get the exact same results. Because experiments weren't replicated properly, that's how we got myths and rumors like vaccines cause autism. One person did one experiment and got their results and published them. And when it was duplicated over and over again by using the scientific method, we found out that those results were a fluke. It only happened that one time. So we have to have this method. This right here definition is what you're going to write down for scientific method. All right, so the first part of a scientific method is a hypothesis. You can obviously see where we're filling in the blanks. You're going to write these definitions down on your notes. So the hypothesis is an educated guess. So the first thing we're going to make is an educated guess. I think a plant is going to grow better in warm temperatures. That's my hypothesis. As you get in more advanced sciences, especially if you plan on going to college, you probably aren't going to have, I think, statements or I think because you're going to move into more blatant statements like the plant will grow better in the garden where it's warm. And then you'll go on to explain yourself with scientific fact research. But for right now, I think statements are completely fine. The experiment is what you're going to do. What are you going to do? Are you going to put one plant in the heat and one plant in a refrigerator? Explain what you're going to do. It needs to be organized and it needs to test and reflect that hypothesis. When you plan an experiment, the main thing you want to have is a control. So a control is a standard for comparison. So if I think hot temperatures are going to make the plant grow faster, I need to leave one plant at a regular room temperature. That way I can compare just how much bigger that tall plant is in the heat. If I put all the plants in the heat and then I put them in the fridge and the plants in the heat are taller, that's great, but are they taller than a plant at room temperature? We're not going to have anything to compare it to. So we need that standard of comparison. The constants are the factors that don't change. I'm testing heat on plants. I'm going to make sure everything is the same. I'm going to make sure their soil is the same. I'm going to make sure the amount of water I give them is exactly the same. I'm going to make sure they're all in the same size pot. I'm going to make sure they all start as the same size sapling. I'm going to make sure they're all the same kind of plant. Because if I plant one sunflower seed and one chia seed, a sunflower can get 10 feet tall and a chia gets 3 inches tall. Now I don't have an experiment because I can't compare them. And if I accidentally give the plants in the heat 3 cups of water one day and I don't water the other ones, did they get taller because I gave them water? Or did they get taller because they were in the heat? We don't know. That's why we have constants. We're going to keep everything constant except for that variable we're manipulating. And that brings us to the independent and dependent variable. So the independent variable is the variable that we're manipulating, that we're changing. It's independent. If you think about like an independent person, there's somebody that goes against the flow and they do what they want to do. The independent variable is the variable that we can change. The dependent variable is the variable that we measure. It's dependable. You can always count on it. So the dependable variable is what we're measuring and counting. So we're going to adjust heat and cold. That's independent. Our dependent variable, what we're going to measure, is the height of the plant. So sometimes scientists can't see everything that they're testing. Sometimes things are too small. We're going to learn about something called an atom. An atom is too small for us to see with our eyes. So we have something called a model. And this model helps us visualize it. You use the same thing in biology when you learned about plant cells and animal cells. Yes, we can see them with our eyes in a microscope, but you can't see all the organelles. You can't see all the parts. So we make them bigger with models. So models are extremely important to science, and they represent ideas and events to help us understand things better, to help us get a visual grasp on them. All right, in science, we have two different things. We have a law and we have a theory. A law is a rule of nature that sums up all the observations. It can never change. Laws are there forever. We don't have very many laws. The best example is the law of gravity. If you drop it, it will fall. We all know this. You start testing this before you even know what you're doing when you start throwing things off your high chair as a baby. When you start dropping bottles and things, you're testing the law of gravity. You don't know that's what you're doing, but that's what you're doing. You're testing the law of gravity. You're learning that every time you drop something, it will fall and hit the ground. A theory is an explanation based on experiments. So if we do the same experiment 1,000 times and we get the same results 1,000 times, we can come up with a theory. One of the most famous theories is the theory of evolution. So we come up with this theory. It's the most logical explanation at the current time. Theories are pretty much 100% correct. They are the best explanation we have with all of the research combined that we have at that given moment. But 20 years from now, technology might advance, and that theory might change. So because it can change, it's a theory and not a law. So scientific laws never change. Because they never change, there's very few of them. Theories can change. Most of what we learn in science are theories. Science has changed from when I took it when I was in high school. Things have changed. Things have progressed. We've gotten more advanced. We've learned more things. So some of those theories are changing. And sometimes theories can be proven false. So we can come back. There was a theory of spontaneous generation. We have a bunch of evidence that say it could happen, and we have a bunch of evidence that says it probably didn't happen, but we don't know. That's what makes it a theory. Science also has limits. So we can't explain everything with science. Scientists will tell you we can. We like to be arrogant. We like to say we know everything and we can prove everything, but sometimes we just can't. Sometimes all we can do is make the best educated guess that we can with the research that's available. And we can give you the best answer we can give you. Will that answer change? Most likely, probably. Before Darwin's theory, there was a guy named Lamarck who said giraffes' necks get longer because they want to reach the top of the tree. And so they think they want a longer neck and they get a longer neck. At the time, that was a limit of science. It's not anymore. So science can't answer all questions. We also can't answer questions about emotions and values. What I might think is beautiful, you might not think is beautiful. I did a research experiment in college on relaxation in dental chairs and relaxation in medical offices and music and how that was tied to it. And what music relaxed me might not be the same music that relaxed you. So we can't answer everything with science, but we can do our best to. So science can be limited. We can push it to its limits. But if we stop pushing science to its limits, we'll never keep learning. So it's our job as scientists and your job as scientists to continue questioning everything around you and to push science to its limits on a daily basis so that you can continue to learn more about this world. Because if you stop questioning, then we'll stop evolving. We'll stop changing. And we need that change. We need new minds. We need new thoughts and ideas because we don't all think alike. All right. If you have finished this, you have finished this lecture. I hope you have a good day, and I will talk to you tomorrow.